So welcome to today's water and wastewater treatment live session, and this is the second week session. I am Saptarshi Bose here, PML research scholar from IIT Madras. So basically, like the last week, we will go through few questions. Some of them will be kind of conceptual or theoretical, and some of them are like numerical. So we try to solve, we will try to clear the concept as we progress. So the first question is the numerical one. I think all of you are now aware of BOD and how to calculate any numerical question regarding BOD. So you can see that an industrial wastewater enters a stream having a BOD concentration of 10 mg per liter and a flow of 20 meter cube per second. If the flow of the wastewater is 1.5 meter cube per second and BOD concentration is 250 mg per liter, then what's the BOD concentration at downstream point? So please use your chat section or the in-call message section to write your option. Okay, I got the first answer from Sandeep. He's saying it's B. So I'll wait for a few more minutes for others to answer. I request everyone to at least participate. And this is a very easy question. Actually, this is the first question. So this is the easiest one for today's session. Okay, 1 more minute. Otherwise, we'll go for the solution. Anyone wants to answer? Okay, so let's go to the answer. Correct answer is D, 26.74 mg per liter. So we will see how to solve this. So BOD downstream is written as Q1 multiplied by Y1 plus Q2 Y2 divided by Q1 plus Q2. So that will be 20 multiplied by 10 plus 1.5 multiplied by 250 divided by 20 plus 1.5. So how this is we are doing basically. This is 10 mg per liter, right? 10 mg per liter of BOD concentration and a flow of 20 meter cube per second. So this is nothing but some mass balance. You know what is it called mass balance kind of thing. So it's not difficult to understand. If you just go by the concept, you will find. So this was the industrial wastewater, right? It was having the BOD concentration of 10 mg per liter and flow of 20 meter cube per second. So suppose this is the Q1, the flow rate, and then Y1, this is the BOD concentration. This is coming from the industrial wastewater industry. And this is the stream. So this is the BOD, sorry, flow rate again, Q. And then this is Y is our BOD concentration of the stream, right? And we are dividing this with the flow. So this is simple mass balance Q1, Q2, and then Q1 Y1, sorry, plus Q2 Y2 divided by Q1 plus Q2. And then we are getting 20 multiplied by 10 plus 1.5 multiplied by 250 divided by 20 plus 1.5, right? So if you do the calculation, you will get this 26.74. And there is no need actually to go for any unit conversion because that will cancel out. So you don't have to go any unit conversion. Just directly you can solve it. As simple as that. I hope this is clear for everyone. So the next question, a theoretical question. When wastewater is disposed into a running stream, four zones are formed, right? In which one of the following zones will the minimum level of dissolved oxygen be found? So maybe the zone of degradation, the zone of active decomposition, zone of recovery, or the zone of clear water. If you have gone through the lecture, I think this one is very much clear for everyone. Basic theoretical question.
Answer is B.
Okay, thank you, Abdul. What about others? Please try to participate. Okay, I got One answer from Ruchita, that is B, right? Okay. Anyone else have any different, anyone else has any different idea, views apart from B, like C, D? Okay, right. And the answer is B, that is the zone of active decomposition. This is the correct answer. So congratulations. The zone of the active decomposition characterized by various characteristics. First, it will be darker or grayish color, and then you will find some foul gases like methane, carbon dioxide, or hydrogen sulfide. And you will also find the sludge coming at the top and forming an ugly scum. And there, due to this scum at the top, right, and very less amount of DO present in the water, there will be no higher life form can exist there. So very minor life form will be there who can survive with less oxygen. So this is the oxygen sac curve. I think all of you are aware of this curve. So how this curve is actually working. This was our initial DO suppose, and then this is the deoxygenation curve with the degradation oxygen level is coming down, DO is coming down, and then there is also deoxygenation due to natural occurrence. It is going up, it is trying to increase the DO level. And if we combine these two lines, yeah, I'll get this line, that is the oxygen sac curve. This is the normalized line from these two. And here you can find after t time or after t distance, whatever you can say, measure with respect to time or the distance. Is the same thing with the flow rate, with respect to flow rate, obviously. So you will find different kind of oxygen deficiency or the or how much oxygen is present. So if I am talking about in terms of this saturation oxygen, then we can find that how this deficiency is going on, and again it is trying to reoxygenate the water. So you'll find different zone. So this is the active decomposition zone you can find. So here also you can find that critical condition is there, or the critical point where the DO concentration or content is less, extremely less. So this is the critical point, right? So that's why you're saying the active zone of decomposition is our answer. So the number three question is again theoretical. The time of BOD degradation in the stream can be affected by ratio of stream depth to flow depth with stream BOD value concentration, BOD degradation rate constant. So you have to find out. I got the first answer from Ruchita, that is B, D. Okay, Sandeep D. Anyone else? The easy one, only theoretical one. Don't waste time here.
Answer is B.
Okay, thank you, Abdul. B. And what about others? Sarala, Shubir, and Jonathan. Please try to participate because this is a easy theoretical question, right? Not a numerical one, and you need a big formula. So we'll go for the solution. The correct answer is C, not B nor D. So this is a 2 and 3. Basically, this one, the stream of BOD value concentration and BOD degradation ratio, rate constant. Why? Because whatever is the stream condition, the depth and flow, it doesn't matter. Whatever is the like this one or the stream width or the depth, it doesn't matter. So what will matter basically? First is your, if you go through this formula, you will get. So this is the BOD formula which we use to find out the BOD of 5 days or 3 days or whatever days I want. And also it is related to the ultimate BOD, whatever the organic matter total present there. And also rate is the main factor here. And also the time. So this upon these two, it will depend, right? So there is no such condition like the depth or the flow with something like that. So it is totally dependent upon the rate of the BOD degradation, that is the K rate constant, and the time taken. So these two factors are there, right? So the next question is, for a wastewater sample, the 3-day BOD at incubation temperature of 20 degrees centigrade is estimated as 250 mg per liter. So the taking the value of first order BOD degradation rate constant as 0.22 day inverse, the 5-day BOD of the wastewater at incubation temperature of 20 degrees C will be what? This one is also a easy one, not a tough question. Taking the value of first order BOD degradation rate cost. You have to just calculate the 5-day BOD. You can refer the formula. Actually, I just showed you the formula in the previous question. You can refer the formula. You can take the help of your note. Yeah. Okay, Ruchita. Yeah. I'll give time. No issue. I request everyone to try. Okay. Yeah. We'll go for the solution, Sandeep, and Ruchita is saying it will be 280, right? So the answer is in between 340 to 355, most probably 345. Please check by yourself because there might be some numerical error. So this is how we will try to solve. It's a very easy one, right? So what was given? That the 3-day BOD was given. 20 degree centigrade temperature, no need to do any temperature conversion. So it was given as 250 mg per liter, and this was first order BOD degradation. Then the rate constant was this one as 0.22 day inverse, that is K, and you need to find out 5-day BOD in mg per liter. Temperature is same, fine. So this is the formula for BOD 5, that is L naught for anything, any BOD 5, 3, whatever you can say. So I'm writing for 5. This is L naught ultimate BOD 1 minus then e to the power minus 0.2, that is the rate constant, right? Multiplied by 5 for 5 days, this is the day, and then for 3 days BOD, I'm getting same thing, L naught 1 minus e to the power minus 0.2 multiplied by 3, right? So if you just divide these two equation number 1 and equation number 2, we'll get this one BOD5 divided by BOD3, and this is something like that. Very easy, right? Nothing complicated. Just cancel it out and put the BOD3 value, how much it is, 250 mg per liter. It was given in the question. So if you just calculate this, you will find the BOD5 as 345.198 mg per liter. So I hope this is clear for everyone, right?
Hello, sir. I used the same formula.
Okay.
What are you saying? Just I think there is some mistake to solve the exponential e power base of something. I am just forget to solve this. E to the power minus two into
Uh-huh.
five. Just yeah, I forget. That's why I
Okay, you
got
got different
wrong.
answer. Yeah, might
Yeah.
be that's why I told you and everyone, like, there might be some numerical error from my side also. Please check it. So I'm not
Uh,
saying that it's
I
correct.
used 0.22. I think
Yes,
that is
yes,
yes.
yes,
I
yes,
think
yes.
the value
That's
will
what.
be some different. Yeah.
Yes, yes.
Okay.
Right, right, right. You are
Yeah.
absolutely right. So please check by yourself. This is the method by which you can solve this kind of problem. But the numerical thing, please check by yourself because there might be some calculation error from my side also. So make sure that is fine. Don't just copy. You can also calculate by yourself. And that's very good, Ruchi. So the next question is the theoretical one. This the BOD test is faster than COD, or the COD test is just like BOD. So what is the correct statements? What are the correct statements, right? The multiple correct statements are there.
Option B,
Uh,
2 and
Okay,
3.
okay, yeah, thank you. Option B. Then Javed Khan is also saying option B. What about others? Write your answer in the chat section. You can use that. Who join later? That's why I'm saying. Okay, Ruchita B. And this is a very easy theoretical question, so I'll not wait more. So the correct answer is C. Please check. Okay, Sandeep is saying also B, but the correct one is C, unfortunately. And what is C? 2, 3, and 4, right? So this, and this. So COD test is just like BOD test, right? And it doesn't measure the oxygen demand due to nitrogenous species. So we will consider only this much. But there is also one thing. This is for the nitrogen species, like nitrite, nitrate. For that decomposition also we need oxygen. But in COD test, it's just like BOD. So it will not measure the nitrogenous oxygen demand basically. Then COD will always be higher or equal to BOD. That's what I told in the last session. Please try to recollect like why COD is equal or higher than BOD, because COD will include BOD as well as something. more than the BOD. And what is that? That answer is in this number 4 option. That COD oxidizes biodegradable and non-biodegradable organic matter. We use potassium permanganate or similar kind of oxidant to degrade biodegradable, this biodegradable as well as non-biodegradable organic matter. So what BOD will do, BOD will just degrade the biodegradable organic matter. But the bacteria or whatever the microorganisms are present there, they will not be able to degrade this non-biodegradable organic matter. So to get how much non-biodegradable organic matter are present in the water, we need COD test. So I think this is clear for everyone why COD is always higher or equal. It might be equal because if there is no non-biodegradable organic matter present in the water, then only biodegradable matter is there. So that in that case, particular case, BOD will be equal to COD. So the next question is the chlorine, again numerical question. It's regarding chlorination.
Excuse me, sir. What is the correct answer of the last question? A, B, or C? The which
Uh,
option was C?
this one C, 2, 3, and 4.
B, B, 2 and 3.
2, 3, and 4 also.
2, 3, and 4. Okay, C.
Uh,
Okay, thank you.
and also don't worry that all the PPTs, like all the in the PDF format, it will be uploaded. I think that NPTEL forum will let you know, so you can later also check whatever is in this PDF. So this question is again the numerical one related to the chlorination. It's a very big question, so read carefully and patiently. So you can refer to your notes or any book if you have to get the formula. No problem, but at least you should try. Okay, we'll go for the solution. So the correct answer will be 67.4 numbers per liter. So we will find how to calculate this. So what is written that chlorine is added to the drinking water to kill pathogen organisms, and after chlorine is fully mixed into the water, it passes to the chlorination chamber. So first chlorine was added, mixed, and then it passes through the chlorination chamber, where pathogens are actually getting killed. The concentration of chlorine is relatively constant. So the concentration of chlorine is relatively constant in the contact chamber, right? So the rate of loss of pathogens can be assumed to be proportional to the number of concentration present. That is the number per volume. So what is it? That the rate of loss of pathogens is assumed to be proportional. This is a very important statement to the number of concentration of the pathogens which were present earlier, you can say, initially, or whatever, even in the time being, if I take the time of t, then also whatever it is present, and with respect to that, we can calculate. So this number of volume, and then assume the proportionality constant as equal to 10 to the power, sorry, 10 hour inverse, right? So this is the proportionality constant for this statement, it was proportional, and then we can find out the flow rate is how much. Flow rate is 0.2 meter cube per second. The initial concentration of pathogen is 10 to the power 4 organisms per liter. So you have to calculate the concentration of pathogens expected in the plug flow contact chamber. So it's in the condition of plug flow water chamber, contact chamber, and the retention time is 0.5 hour. So all those data were given, right? And yeah. So this all the data actually is given for two different questions. One is this one, and another is the next one. So it's the combined question. So I'll give you chance to check. So here you can write as dc by d theta equals to kc. How it is happening? The change of the concentration of the pathogen, or is, and this is the change of time, right? You can write it as theta, or you can write it as dt, right? Dt or d theta, same thing. So this is the rate of change, dc by d theta or dt, whatever you can write. If you write d theta, that's fine. So this is the rate with respect to time. What is the definition of it? With respect to time, what is the change? So this is the, with respect to the small time, the change of the concentration of the pathogen, that is the dc, right? And this is proportional to what? The initial concentration, right? And if you want to equalize, then you need what? A constant, right? A proportional constant, that is k, and then we are writing as dc d theta equals to minus kc. Why minus? Because it is actually going down. The concentration is going down. Initially there was, suppose there was 10 to the power 4, that was the scenario, right? Initial concentration, yes, initial concentration was 10 to the power 4, and then after some time, if you apply chlorine, chlorine will kill the bacteria or the pathogens, so the number will decrease, right? After some time it will be something around 10 to the power 2. So that's why it is decreasing, that's why using the negative sign. So if you just integrate this, I think all of you have gone through the lectures, you know how to integrate this with respect to time. So the time will be from 0 to theta, or 0 to t, that will be the limit for the time for this d theta. And what will be this for C concentration, that is C naught, that was the initial, and then C or CT, whatever you can write. You can write as CT or C, only C, fine, no issue. So after the integration, you will find this, right? After the integration, I am getting this equation, and this is for the first order. And then just you have to put the value, right? C naught was the initial concentration, was written as 10 to the power 4. It was given, right? That was the initial concentration of the pathogen, 10 to the power 4. Then this exponential, I'm writing in this form because I am not like writing in the particular this form. That's all. Minus 10 multiplied by 10 to the power 5, sorry, 0.5, now 0.5 hour. So 10 was the rate constant, right? Uh, yes, 10 hour inverse was the rate constant, and here the retention time was 0.5 hour, right? So I'm just putting the values. I'm getting CS 67.379 number per liter. I hope this is clear. And there is a second question from the same data you have to calculate. So I can switch back to the data screen. So you can write down your data. Just try to see what's written here. Calculate the volume required in the plug flow contact chamber to achieve the effluent concentration of, sorry, there will be no and, to achieve effluent concentration of 1 microorganisms per liter. So that is the question. We have to find out the volume required for the plug flow contact chamber. What is the volume in the unit of meter cube to achieve how many or how much concentration of the pathogens, that is 1 microorganisms or 1 organisms per liter. So this is the basically question. To find the volume, this is the data. Same concept, same equation you need to use. So I hope all of you can calculate this. Already we have done the half portion of this problem. I'll wait for 1 more minute, then we'll go for the answer. Okay. Okay, we will go to the solution. So this was our question. You have to find out the volume required for the plug flow contact chamber. So same equation what we wrote in the last question. It was C equals to C naught e to the power minus k theta. So now you have to find out first what is the theta time required, right? So you know what is the concentration, initial concentration C naught, that is 10 to the power 4. What is our desired final concentration, that is 1, right? So ln and divided by that, the k was 10 our inverse. So I'm writing this, and I am using this log n natural logarithm or ln to neutralize the epsilon, right? So that's how we will calculate. All of you were aware how to calculate this thing. Nothing new. So the theta I'm getting as 0.921 hour, right? So this is the time required to achieve the concentration of 1 microorganisms per liter. Now theta is nothing but V by Q, right? So what is V by Q? V, because this is the retention time, hydraulic retention time. Basically, you can find out that this is a plug flow reactor, right? What is coming and what is going from this position, and it is going out from this portion. So you need to spend that much amount of time, right? Suppose there is some water. Suppose I have some area or volume of water coming, just entering to the system, and it needs to be there for how much time? 0.921 hour, right? So for that much time, it needs to spend inside this chamber to get our desired concentration of water, right? That's the main concept. So this is the hydraulic detention time. This is nothing but the volume divided by the flow rate, Q. So we know the flow rate here. Right? It was given, I guess, somewhere, the question, or I missed the data. Point two, yes, the flow rate is given, right? Flow rate is given at 0.2 meter cube per second. So you know what is the value of Q, 0.2 meter cube per second. This is our theta value. Then we can find out what is the volume, right? And this is a unit just conversion from second to hour, 3600. So I'm getting volume as 663.12 meter cube. Then again a theoretical question. Eutrophication in water bodies is called by what? The discharge of toxic substances, excessive discharge of nutrients, excessive discharge of suspended solids, or the excessive discharge of fluid.
Option B.
Okay, thank you. So I got my first answer as option B. What about others? This is a very easy, common question, very popular question, different examination. Okay, Ruchita, you're also saying B. Sandeep B. Anyone else? Okay. right? B is the correct answer. Excessive discharge of nutrients. So for this, we can get this eutrophication, and it will also uh, create problems. It will also increase the algae growth in the water, and it can be from different sources like point or non-point sources, from direct source or the indirect source, like water. Water was having some organic matter or nutrients. It was coming from a very far, or it might be some point source. So select the correct statements regarding CSTR and PFR. I hope you know what is the fluid form of CSTR. What is the plaque flow reactor PFR? So you have to find out the correct statements. Okay, I got answer from Ruchita C and Javed Khan B and C. Again Ruchita C and D. Anyone else? Sandeep C. Fine.
B and C.
Okay, B and C again from Abdul. Fine. Okay, Saravanawala B and C, right? So let's discuss the solution. So the answer will be C and D, not B. See, this one totally incorrect because in PFR it is vertically mixed but not horizontally. So it's not uniformly steered or mixed. Then in case of CSTR, what happens that once the concentration is coming from this place and I have the continuous steering equipment, so just after this coming, it is getting the same concentration everywhere. So the concentration is same here in CSTR. So there is no change of concentration with time because after just entering into the system, it is getting mixed and there is always a constant concentration. Then C, this one incorrect, C and D. In PFR, the concentration varies along with the length of the reactor, obviously. So it will vary something like that. When it was entering, it was higher. When it was going out, the effluent is lower. So it is with the length of the PFR, plug flow reactor is varying. Then PFR are more efficient than CST at the same hydro retention time because of the concentration gradient. Here the concentration gradient is very less because after coming here only it's getting mixed. But here you can see the concentration gradient is high. So there is a concept, I'm not talking it in details. So you will just learn that with the concentration gradient, if that the concentration gradient is higher, change is higher, then the degradation rate will be higher. So that's why with the same retention time, the PFRF is more efficient than CHTR. Again, a numerical question related to BOD or DO measurement, sorry, BOD measurement basically. So the initial DO of mixture of sample and dilution water is 5.25 mg per liter. Final DO of the mixture of the sample and dilution water is 3 mg per liter. The BOD test is run by adding 2 ml of wastewater to 300 ml BOD bottle. Assume dilution water has negligible oxygen. Don't have to count that. It doesn't have any organic, means that it doesn't have any organic matter present in the water, the distilled water. So the BOD in mg per liter you have to calculate, and that's BOD for the wastewater. How much BOD was there?
Is the answer 337.5?
Okay, 337.5. Thank you. Thank you for your answer.
Thank you, sir.
Yeah. Yes, I got answer from Javed. Also, Ruchita also 337. Okay, so we'll check. Yes, correct answer 337.5. So all of you have done this correctly, but just for others understanding, I'm just telling once more. So BOD is given as DO initial minus, this is the DO initial minus DO final, and divided by the dilution factor. So the DO initial was 5.25 mg per liter, and then the final was 3. So I am just putting the values, nothing else. Then the dilution factor, how we will calculate the dilution factor, 2 ml of wastewater was added to 300 ml of BOD bottles. So 2 ml of wastewater and total volume was 300 ml. So 298 ml of distilled water or the pure water was there. So the dilution factor will be 2 divided by 300, and I am getting as 337.5 mg per liter. Then the next question, again related to BOD. For a waste, the 5-day BOD at 20 degrees centigrade is found to be 250 mg per liter. For the same waste, 5-day BOD at 30 degree will be what? Again, it's not numerical question, basically conceptual question. You don't need to calculate, just you have to answer.
Option B.
Okay, option B. Good. Very quick answer. Thank you for that. What about others? Okay. Yeah, I am getting some answers. Yes, Javed B, Ruchita B, Sandeep B. Fine. Yes, the correct answer is B. It will be more than 250 mg per liter because as temperature will increase, all of you know that the metabolism of the organisms will also increase simultaneously, right? So what will happen? The 5-day BOD will increase. So like if there that is that for 20 degrees centigrade, this is this much 250 mg per liter. Then if the temperature is 30 degree, 10 degree more, then it will be the faster reaction. They will consume the BOD faster. The microorganisms will consume BOD very fast. So that's why I will get the data much higher than 250 mg per liter. But the ultimate BOD will be same. That's the concept because that will not change. That much of organic matter is present, right? You can change temperature whatever you want, but that will be same. So the a wastewater sample has 4 days 20 degree BOD value equal to 75% of the ultimate BOD. Then the rest constant you have to find out. And the base is E per day you have to find out. Very easy question, same old formula of BOD. Just you have to find out the rate constant. That's it.
Point 346.
Okay, 346 quick answer. Thank you. Very good. Ah, 1, 3, 4, 6. What about others? Let's wait for 2 more minutes or 1 minute is fine, I think. Very easy one. Just use your calculator and answer. Okay, we'll go for the answer of the solution. So the answer is in between 0.34 to 0.35. Yes, there might be some calculation error from my side, so please check. So minor error will be there. So the main concept behind this, nothing but the same old formula. It was given for 4 days BOD, not 5 days. Same thing. It doesn't matter 4, 3, or 5. So the same formula 1 minus BOD 4 divided by BOD ultimate. I am writing in a different format only. Don't worry. The same thing BOD equals to L naught 1 minus E. And here e to the power minus K multiplied by 4. So this was the original one. And from here I am getting this. Then just you have to find out K, right? So K will be nothing but I'm taking again ln log. So to eradicate, to remove this epsilon, this is 1 minus 0.75 because 75% of the ultimate BOD was 4 days BOD, right? So that's why I am writing in this decimal format 0.75, 1 minus 0.75 divided by 4, and you just calculate, you will find around this 0.346 day inverse. Please do it by yourself, check whether it's correct, value is correct or not, but the method is correct. So the next question, this is the common data question again for the next two questions, 13 and 14. In a batch reactor, an experiment is run in the lab to remove a toxic compound, and that is called TMDD. Is this the story? And the initial concentration is 15 mg per liter of TMDD, and the concentration after 3 minutes was found out as 2 mg per liter of TMDD. Assume that TMDD can be removed by a process which can be described by first order rate reaction. So few important things are there, or few important data are given. First of all, it is done with a batch reactor experiment, and it was found as the initial concentration this much, concentration after 30 minutes this much, and it was written as it will be in the first order rate reaction. And this is the first order rate reaction, right? We all know that is R loss, or how much TMDD actually loss means how much TMDD is getting reduced or degrading, equals to K multiplied by C, concentration of TMDD. That is the key formula or key expression, mathematical expression of first order reaction. So now the question, please pardon, this question 13, that the assuming steady state and the treatment system is a plug flow. Now it was done in a batch reactor, and you have to find out for plug flow reactor, calculate the hydraulic retention time which would be required to achieve the effluent concentration of not and the effluent concentration of 1.5 mg per liter of TMDD with the same initial concentration in the experiment. So you have to find out the hydraulic retention time in minutes, right? That is the question. I will wait for 1 more minute and then I'll go because we are running out of time. Okay, so this is how we'll try to solve this. So if we do the mass balance for the batch system, the same thing I am getting Ct equals to C naught e to the power minus Kt. Same for every equation, whichever is the first order equation. This is dC by dt equals to Kc and then integrate and you will find this one. You will find the similar kind of equations everywhere. So now the input is here for batch experiment. Ct was 2, right? After 30 minutes, it was 2 mg per liter. Initial concentration was 15 and T was 13 minutes. So if you just put all the values here, Ct value, C naught value, and T value, you will get K as 0.0672 minute inverse. Fine, that is clear for everyone. Then next, we'll go for the plug flow system. So in case of plug flow system, similar kind of equation we will use. There is no change for first order plug flow system. Same as the batch version. Pardon, this will be like not only. So C theta equals to C naught a multiplied by e to the power minus k theta. Just put the value here. What is my desired concentration? My desired effluent concentration from the plug flow reactor is 1.5 mg per liter, right? That is my desired concentration. So C theta will be 1.5. C naught is 15, same as the initial concentration. K calculated here, that is 0.0672 minute inverse. We will get theta as 34.26 minutes. So that much minute will require for a plug flow reactor to get our desired concentration of 1.5 mg per liter. I hope this one is clear. So the next question, totally similar kind of question with the same data. You can refer to the data, previous data. Assuming steady state and treatment system is completely mixed flow reactor. Now the last question, it was plug flow reactor. Now it's a mixed flow reactor. Calculate the hydraulic retention time which would be required to achieve the effluent concentration of 1.0 and 1.5 mg per liter TMDT. Same thing, only the reactor is different here. Earlier it was plug flow, now it is completely mixed flow reactor. So what is the hydraulic retention time required? Let's try to do it quickly. Only need to change one equation. That's it. The rest will be the same. Okay, we'll go for the solution. So we already calculated what is the K value, rate constant value, that is 0.0627 minute inverse. Then you have to use this equation. This is for the first order reaction, first order rate reaction for CSTR system, mixed flow system. You can refer to the lecture. I will not like discuss on how these formulas are coming. You can remember this formula, and better not to just remember, go through the lectures, try to understand how this formula is actually coming, how we are getting these equations, right? So then the professor discussed how we are getting this equation. And sometimes you have to remember the equations also. Like when you are trying to quickly solve the numericals, you don't refer to the theory, so you have to remember the formula. So this is the formula for CSTR, for first order rate reaction. C equals to C naught by 1 plus K theta. Just put the values here. C 1.5, C naught is 15, same thing. K is 0.0672 minute inverse. Only the formula is different. I'm getting theta equals to 133.92 minutes. Please refer to the note and you will get it. So the next question is, select the correct statements regarding BOD. Varies with temperature, self purification in the stream doesn't depend on the BOD rate constant. Second stage BOD is due to nitrification demand. For the ultimate BOD, value of the waste remains same at all temperatures. A very good and easy theoretical question. Please answer quickly. Okay, Javed A and C and Ruchita C. Fine. So the correct answer will be A, C, and D also, because that the BOD rate constant varies with temperature, right? You have done similar previous question. So there we saw that with the rate, with the variation of temperature 20 to 30 degree, rate constant was going higher, and that's why you were getting the BOD value higher than 250 mg per liter, right? So, and the C, second stage of BOD is due to nitrification and demand. That's what I told you. First stage is for organic carbonaceous matter, and then the nitrogenous demand. So C and then the D, ultimate BOD value of a waste remains the same at all temperature. So BOD 5 value may change, BOD 3 value may change, but whatever is the BOD ultimate value, BOD ultimate will be always same for all the temperatures, because that much you just have to know the concept behind this, that that much of organic matter is present inside the water, so it will basically not change. What will change with the temperature variation, the rate will change, and you may find out different variation in BOD 5 or BOD 3 or BOD T, better to say for BOD T. But how if there is only 10 mg per liter of organic matter, then it is impossible, right, to get something higher, 20 mg per liter, right? If bacteria or the microorganisms are eating faster, then they are consuming the dissolved oxygen faster. You can get BOD-T higher or lower. That is BOD-T means BOD 3, 5, 2, or whatever it is. But At the end, it will be 10 mg per liter only. So it cannot be 20 mg per liter, right? So the next question is BOD is referred to COD as the index of sewage concentration because very easy question. What is it? Okay, Ruchita D. What about others? Okay, Javed C and Ruchita P and D. Fine. So the answer is C. BOD relates specifically to perceivable organic matter, which is most objectionable sewage constituent because it will create some odor, bad smell, and BOD test is easier to perform and gives more reliable result. No, it's not that much easier to perform. Then BOD represents both carbonaceous and nitrogenous organic matter, while COD no, it's completely incorrect. And then COD relates to impurities which can only be removed by chemical treatment. No, that is also not true. So the next question, numerical one, same as the first question. Right? Please calculate it fast. The first question we have done in today's session, the same thing. Please do it quickly, even within 1 minute. So do you want any more time? It's done. Same was the first question. Wastewater flow rate and the concentration, then river DO concentration, river flow rate, same thing. Okay, we'll go for the solution. So same thing, DO mix. I have done. I showed you in the first question how you have to do. This is nothing Q W multiplied by DOW plus QR multiplied by DOR divided by QW QR. So Q is the flow rate, right? Flow, and this is the DO concentration. This is flow and this is DO concentration. So QW is the flow rate of the wastewater. Yes, this is the flow rate of the wastewater. This is the DO of the wastewater. This QR is the flow rate of the river. DOR is the flow rate, DO concentration of the river. So we are doing this summation and then we are dividing with QW plus QR. A very simple thing, no difficult concept is there. So that's how I am getting DO mix. After mixing, what will be the DO concentration, right? So it is just you have to put the values. 1.2 was the discharge rate, meter cube per second, and 2.5. So 1.2 into 2.5, and this is 8.7 into 7.8. And divided by the same thing, I'm getting 7.16 mg per liter. So I hope this one is also clear for everyone who understood the problem. Thank you for attending today's session.
Thank you
So
so much. Thank you so much, sir.
thank you, Ruchita. Thank you everyone for attending today's session. I hope you enjoyed and learned many things. So we'll meet on the next Tuesday, the same time. Thank you.
Okay, thank you, sir.